Thank you very much for joining us. So my name is Casey Stella. I'm a principal software engineer at Hortonworks here, and I'm the VP and PMC member of the Apache Metron project. This is my colleague, Mike McClavick, who is a staff software engineer here at Hortonworks and a PMC member and committer at Apache Metron. So before I get started, I just want to kind of get a show of hands. How many people know what Apache Metron is? Do you raise your hand? Everyone knows, almost everyone knows what Apache Metron is. That's fantastic. So how many of you are doing cybersecurity right now? You're in this space and you're working toward it. You're working in this space. Awesome. Awesome. So hopefully you're in the right room. So that's fantastic. So today we're going to talk about how to do typosquatting detection with Apache Metron. But really what we're going to talk about through the lens of a use case is how you use Apache Metron to do some non-trivial analytics, right? And to kind of get a flavor of the way that we approach in Metron how to do those kind of analytics, right? This is going to tie into another talk that's going to be given tomorrow about the profiler, which I'm going to be giving. So I would suggest that you attend. I'll show you the connection points during the talk here. All right. So first off, kind of just to touch base, what Apache Metron is. So we're a cybersecurity analytics solution built on top of Hadoop. So what I mean to say by that is that we provide a scalable, advanced security analytics framework to offer a centralized tool for monitoring security and analytics. All right. So what that means is we have built an application on top of Hadoop that is integrated into Hadoop, integrated into the big data stack, that is providing a point-wise solution. All right. So at the end of the day, when I joined Metron, I didn't really have a cybersecurity background. I approach this, I do a lot of the data science on the project, and I really approach this as a more traditional anomaly detection problem, because at the end of the day, what we're trying to build is a framework for finding anomalies and doing it in a way that reduces false positives, all right, as much as possible to help security analysts find the bad guys. And in previous life, I was doing medical analytics, where it was helping analysts find the sick people. I don't want to equate bad guys with sick people, but same kind of idea. You're trying to find the thing that doesn't look the same. What about this doesn't look right? So how we got here was Metron was started by Cisco in 2014 as OpenSOC. So they actually did a presentation here back then it was called Hadoop Summit, and I attended in the audience. So one of you could fork Metron and start your own, just follow in the footsteps, I guess. But it was called OpenSOC, and Cisco actually built a product around it and an open source offering. They kind of moved on, and we took the open source product and we brought it inside of Hortonworks, and we said, we think this is a use case that deserves a solution on top of Hadoop. And we want to go a slightly different direction. So if you were familiar with OpenSOC, what we do is similar but a little bit different in philosophy. Okay? So we graduated, so we submitted to the incubator in 2015, and we graduated as a top-level project in 2017 in April. So we were very, very proud about, and it was an extremely long journey. So we've had a number of releases at this point, both in the open as well as as part of HCP inside of Hortonworks, internal releases, largely based around Apache releases. So it's been really an amazing journey to see Metron grow from what is a fork of OpenSOC all the way to its own very distinct solution for doing this stuff. Okay, so what do we use? So we aggressively use Hadoop. We use Zookeeper for distributed configuration management. We use Kafka as our data bus. Right now we're a Kappa architecture for those of you who care about such things. We are aggressive users of Apache HBase. So, and you'll see that come up in a later part of this talk as well. We use Storm as our stream processing framework. We're aggressive users of Storm. We've been through, both of us could tell you battle stories about tuning Storm in production. Like it's a thing. It's a thing. HDFS for long-term storage, though we work with HDFS compatible file systems as well, or API compatible. We use HDFS for long-term storage of data that flows into Metron. So the idea being that you would send raw telemetry data, we process that, we enrich that to provide as much context as possible, and then we can save that in long-term cold storage for further analysis with Spark or Hive, and real-time analysis inside of a real-time indexing layer. And the indexes that we support right now are Solar and Elasticsearch. Elasticsearch is one of our first. We made that decision because it was the decision that was made with OpenSock as well. We have since started to support Solar as a first-class citizen. And we're very proud to support Solar. Like our most recent release is about our more robust Solar support. And we stitch all of these things together. So those are all a bunch of components, right? Really makes an application as a layer on top. So we stitch all of these components together and these solutions together with a rules and enrichment language called Stellar, which you can think about as Excel functions for streaming data analysis. So it'll go and interact with HBase. You don't necessarily need to know that HBase is under the hood when you do an enrichment that's put into HBase, right? All you need to do is to know that you call the enrichment get function in Stellar, right? And you can compose things, and you can do simple math and rules type semantics. And on top of that, we built a UI because there's not what we realized was building a framework, building a platform is not building a solution, right? You need to build a UI around that in order to really present that to security analysts. So this is what the UI looks like. This was from a demo that I gave last year, looking at the Los Alamos National Labs dataset, authentication records. So Los Alamos National Labs opened a dataset of authentication records and NetFlow records, as well as DNS queries, as well as DNS records for a year of their operation, I want to say. And along with red team events. So someone went and analyzed and said, okay, this person broke in from this machine into this machine, right? So what we wanted to do was to analyze that with Metron and see if we could recreate the red team event. So what we were doing was here, we're showing off the profiler, which is I'll talk about tomorrow, to do things like statistical, to capture statistical distributions of events. In this case, the number of distinct machines that a user logs into, and look for anomalies in those, right? So we see here that these are the alerts. So you could think of this dashboard as a way for analysts to really kind of spelunk in the data. These are the alerts. We have a score that indicates a potential threat. And the threat is the distinct number of machines that user U22 attempted to log into is more than 5 standard deviations away from the median. So that brings to bear context. So Metron is all about bringing in stream as much context as possible. So what I mean by context, things like your asset database, right? Is this machine a web server? Is it a DNS server? Is it this? How should this act? Both, in another way to build context is machine learning models, right? I train machine learning models. I've captured a certain amount of state, and I want to bring that. I want to treat those as oracles that I can inquire about. Things like, is this a domain generated? Is this domain a domain generated algorithm, or from a domain generated algorithm? Likely, or is it a real domain? Okay, so I built this table of the different ways. So really what Metron is about is enrichment and bringing in as much context into the data as it flows by as possible. So, so if you have static data like exports from an asset from an asset database, you would use an HBase enrichment. So you export that. It's a key value lookup semantic, right? This host is a DNS server. right? We build tooling around importing that kind of thing into HBase and using HBase to enrich that as the data flows by as a scalable solution. For slow-moving data, you can use what's called the summarizer, which I'm going to talk about later in this talk. That's our typosquatting solution in part, to kind of demonstrate that. If data is flowing in, like I want to find the association between a user and which machines they've logged into, so I'm pulling in authentication records, but I want to use that information in another stream as it flows by, like, for instance, DNS records, right? I want to be able to use, okay, I know these users have logged into this machine, and I have an IP address in this other data source. That's a streaming enrichment. You're going to constantly stream updates into HBase. But the read semantic, so that's a different write semantic from the top, the static slow moving with HBase enrichment, but the same read semantic. I'm still interacting with HBase there. So use the same stellar functions around that to provide a unified kind of experience. And then if you can capture state in terms, if you can capture context or state in terms of a machine learning model, we have a model as a service where you can take your machine learning model that your data scientists have written in whatever language they choose, as long as they can pen it up in as a REST interface, and they can deploy that on Yarn, and we can interact with that machine learning model in a scalable way. And then finally, we'll talk about the profiler tomorrow, but all of these things are the scope of an event, are the scope of our global scope, right? As the event flows by, I have as much information, the event triggers it, right? The profiler is a multi-event system, so it can do things like time. It can capture state across time. For the last 15 minutes, the number of logins were this. I want to capture that, et cetera, et cetera. Okay, so now on to typosquatting. Okay, so with that context and what Metron does and how it's related, well, let's talk brief about this kind of attack. So typosquatting is a form of attack that utilizes typos in URLs to trick users into clicking on malicious domains. So this is a common thing that spearphishing attacks and phishing attacks use. So if you're super hyper targeted into a particular person, you can construct a domain where there's an easy typo or looks very similar to a domain that they go to, like maybe their bank, right? Instead of Citibank, they'll transform the I into an L, right? So it doesn't arouse suspicion. So this is a fairly common thing that people do. The typical types of typos, boy, say that 5 times fast. Typical types of typos targeted are homoglyphs, so letters that look similar in ASCII or otherwise, right? And especially around Unicode, all right? That's the big one, because there are lots of Unicode characters will look like ASCII characters, and they're very tricky. Subdomains, so Amazon, which goes to am.az.on, that kind of thing, and kerning errors. So kerning M's look like an R and an N if you're not paying attention, right? So generally, it's used to target people, right? So the general approaches to figuring this out in most SIMs, it seems, are generating a set of typosquatted domains for known good domains. The trick about this is figuring out what known good domains are. So for our purposes, we'll consider like the major domains that one goes to, like the Alexa 10,000 or OpenDNS has a list. Like you can get lists of like major domains they're quite popular that you want to use. But also for an individual, so that works quite well for phishing attacks, things like that, especially if you bias it toward banks and stuff like that. But for spearphishing attacks, where it's more personalized, where the attacks are more directed at an individual person, it really becomes a challenge about keeping that list up to date. More on that later. So you generate a set of typosquatted domains from the known good domains, right? So you generate all of the kerning errors and the homoglyph type errors, and then you have a big set, essentially. A very big set, because there's lots of different ways to screw up a domain and make it look like, to construct a malicious domain that looks like a legitimate domain. So one of the challenges around that is scale, right? So the potential solutions, if you're using a database, that quickly becomes untenable, especially if you're talking about the Alexa 1 million or the OpenDNS, and you have a lot of these guys. So for even modest numbers of domain, for the top Alexa 10K, we found, looking at a common typosquat generation program called DNS Twist in Python, it was around 3 million potential typosquatted domains. That seems like a small number, but if you look, you really kind of need more than the Alexa 10,000, right? And the other problem is recency and targetability, right? That's for general purpose data sets. You want to be able to capture that going forward for your organization and for your system, right? What are the domains that people go to legitimately in your system? Okay. So this kind of problem falls into the broader category of enrichment. So we ingest DNS logs or whatever kind of logs that have a URL. And for each DNS log, we want to tag the domains visited as potentially typosquatted. So I want to take the URL, extract the domain, pull off the top-level domain, and take the actual domain itself along with all the subdomains and see if it's a typosquat of one of the known malicious domains, either from a reference data set like Alexa 10,000 or from a data set that we have constructed, or in addition to a data set that we've constructed for our organization. All right. So there's two ways to handle this inside of Metron. One is a basic HBase enrichment, which you can certainly do. And the other one is a summarizer, which is, I think, slightly more clever. Okay, so let's start with the HBase enrichment, very simply. So we treat HBase as that table. So first we use a program like DNS Twist to generate all the typosquatted domains. All of those are keys, right? The key is the domain. So you could think of the HBase table as just a giant set. And you can interact with that HBase table through Stellar. And this is the Stellar expression here. Enrichment exists. So it's an existence query inside of that HBase table. So my enrichment type is typosquatted domains. The table is enrichments, and the column family is T. And I'm going to bounce the IP destination address from that, assuming that IP destination address is the domain with subdomain stripped and TLD stripped. And if you don't have that in your raw data, you can use Stellar to generate that from an existing URL, right, or an existing domain. So the problem is, there has a couple of issues. One is it relies upon a pass over the data locally with DNS Twist, right, which is not terrible, but it is still a thing. And the other thing is, depending on how often we add new domains, this table could get quite large. But HBase is a scalable data store around key value semantics, and we are using key value semantics here. But the real problem is we have to keep the table up to date with known good domains to catch kind of the long tail and the more targeted solution for your organization. So this is a perfectly reasonable approach to doing that, one which we're not going to necessarily show. Instead, we want to show a different approach. So because this problem boils down to constructing a set inclusion, one of the core philosophies of Metron is that we are really big into sketching algorithms and summarizing. So one of the ways to do that efficiently is a Bloom filter. So can we take this data and construct a Bloom filter out of it with just the raw Alexa 10,000? And can we use the profiler to fill in the gaps of the more recent data, the more recent domains that people have attempted to go to? So the real question it boils down to, are we willing to accept false positives, and to what degree? So with Bloom filters, you're going to get, you may end up with some false positives, but the nice thing about it is you can control that rate, right? The summarizer is a utility that we've constructed in Metron that will allow you to use Stellar and use the tools inside of Metron to build this summary object. Specifically, in our case, it's a Bloom filter. It could be another kind of summary object, like a statistical distribution, or using T-digest, or a hyperlog log plus for doing things like cardinality checks. But in this case, we're using a Bloom filter. And we're going to write that summarized object to HDFS. OK, so what it's going to look like instead of that enrichment get, it's going to look like a Bloom exists, and I want to get the object to the serialized filter. All right, and I want to pass in the IP destination address. So if it exists in that filter, then I want to consider it a Bloom. I want to consider it typosquatted. And furthermore, now that we have that Bloom filter, we can interact with the profiler, which is also going to be capturing summaries of domains that were visited more than k times in the time range of your choice. And the idea being, if I'm visiting this domain several times, or if multiple people are visiting a given domain several times, then it's likely a legitimate domain, right? So if you union those two Bloom filters together, and then ask of that unioned data source, you get a very robust solution that works well with reference data along with the data that flows by that is happening right now. So it's a more complete solution. In the future, we'll be adding some other sketching to make this kind of query a little bit easier and more scalable, specifically stream summaries. OK, so I'm going to pass to Mike, and he's going to do a demo to show you kind of how this works with Metron.
Hey everybody, I'm Mike McClavick. Going to walk you through real quick. Let's see here. Go a little bit larger. All right, so what I'm going to show you kind of is a rundown of what Casey just talked about. So we've got a few steps that, in order to get this to work, we have to accomplish. We've got to create this summary object that he was talking about. So again, going back to the Bloom filter, the idea here is that instead of using HBase, we're going to use this summary object. So it's stored, it's something that we end up pulling from the Alexa top 1 million list of domains. We summarize that and we store that up in HDFS, so it's available anywhere in the cluster. And so what we end up doing there, again, we extract out the data that we care about, store it as the summary object in HDFS, and then we have a Bloom filter, which is a way for us statistically, again, to be able to see whether or not we have a hit against this object. So instead of having like a concrete list of values that we compare against, we actually have something that scales a little bit even better than what we would have before. So I'm not going to run the commands. And in fact, for this demo, we didn't import the entire million. If you want to do that kind of thing on your own time and have your company pay for a longer bathroom break, you can run all million. But for this, we basically...
So just to get kind of a general sense of how long it takes. One, it's a MapReduce job. It'll run as a MapReduce job, so it will scale out linearly. Two, it will take the Alexa 10,000 and balloon that into around 3 million actual inserts into the Bloom filter, and it takes around 15 minutes on a VM on my laptop. So the 1 million should scale into a more reasonable approach.
Yeah, so what we did here, we took the top 10K, again, just to be somewhat expedient with time. But just to show you the output, basically what happens when I run this, we get, in processing 10,000 records, we get somewhere in the magnitude of, as Casey mentioned, 3.5 million records that I'm getting put in this Bloom filter. And these are, again, stored up in HDFS. Give it just a second to connect. OK. So what I've done here, I have what we're looking at here is the Stellar REPL. This is a useful command line tool that is built around the ability to run your functions in Stellar. Again, we call this somewhat like Excel functions of sort. So what I did earlier was ran some of these commands against this object store in HDFS. So what I'm looking at here, there's a Bloom exists with an object get. The object get extracts back that data or the object from HDFS, and then I can compare it with the Bloom exists against the value that I pass in here as an argument. So if I pass in Google, now it's going to take a minute on the first run, and it says true. So this effectively says, hey, this looks like a typosquatted domain based off, again, that Alexa the top 10,000 that we pulled. Google would, of course, be your expected. So if we do type in Google there, should return false. Notice how quickly that returns back. So as you're executing this in your environment, you have Metron up and running. Realize this gets cached off. This object gets cached off in the enrichments, and so when you're doing your threat intel and triage, that's not going to need to load that from HDFS every single time. It'll load as necessary.
So the nice thing is, over the HBase solution, is you're not having to go outside of that node in the cluster, right? You're able to introspect the cache, and the memory size is kept small because a bloom filter is a much abbreviated data structure. It's not going to scale linearly with that 3.5 million input size.
Yeah, so you get a few variations, Google, things like that. So yeah. Now, just using that as an example, we ran, again, some of this data through through Metron here. So I'm going to show you, I've already done some pre-filtering here based on what we had set up for this demo is we pulled in, set up the Squid proxy server. So I ran some commands through the command line just to get the data into Metron, do the parsing, and get the alerts triggered off based on the bloom filter that we have for the typosquatted domain. So you see a couple things here. I've got, what I did was I ran this against github.com and then github.com. And so you can see here it's a little bit small, but the non-alerted record here is the github.com record, as you would expect. And then the one that we have up here that's got a score of 10. If I roll over this, then you'll see, well, I'm just going to pull this up here. It's a lot easier to see that. So the domain without the subdomains is github. So this one, as we would expect, was flagged as being a typosquatted domain in the alerts UI that we have.
Can you show them the REPL with the domain typosquat? So we actually ported DNS twists into Stellar. So it's able to run locally inside of Stellar. We ported the algorithm itself. So
yeah.
These are, sorry, go ahead.
Yeah, I was going to say, so what we're seeing here, this is effectively what we ran when we generated that object that's stored in HDFS to begin with. So this is going to be all the possible calculated typosquat domains from Google. This is basically the entire pool that, again, based on these rules and the different types of typosquatting you've had, bit sitting and all sorts of different type of typosquatting approaches. This is the list that's generated from that. So across all of those domains that we pipe into the system, it's going to generate this massive bloom filter from this sort of listing. So this is effectively what we're mapping against and running that query and saying, hey, do I exist in this set? So again, as you see at the beginning here, you've got like the, what is that, umlaut? Yep. Google there, and then Google and some other really crazy wild things. Again, subdomain type of squatting that you see right here, misspellings, Googla, Toogle, so on and so forth. So this is really fundamentally what we're basing this around. And again, this is from the DNS twist library that we pulled in for doing this type of typosquat generation.
So we ported it in, and going forward, we can choose to enhance this to, if there's new types of typosquatting approaches, it's as easy as adding a little bit of code into Metron for us to support it. And I think with that, yep. Take some questions.
Questions.
We have plenty of time for questions, a little bit over, almost 10 minutes.
So I think DNS twist would also account for the case where you type Google correctly, but the bit flips and transfers.
Yes, we do. Yes, yeah. That's a very good question.
Yep.
Yeah, so we do DNS twists and Metron both support
bit squatting. Bit squatting, I think.
Bit squatting is what they
yep.
called it. Yes.
Okay, so you're looking at the response message to catch if that actually happens. The response comes back.
Yeah, if someone is targeting a bit squatted domain, if that's the type of typosquatting they're doing, this should catch it. Yes, absolutely.
Yeah. And again, that all ends up in the bloom filter. So again, the false positive rate, these are all things that you can tweak based on how you generate your bloom filter. And again, you can generate that filter from any number of domains that you want. So again, we just, for this example, to keep it tight, took 10K of the Alexa top 1 million, but you can add your own, of course, as well.
Good question. Yes.
I want to ask on two perspectives. One is the learning curve of the Metron.
Oh, what's the learning curve for Metron?
Sounds to me you talk about a field like enrichment. I think that's something very specific to Metron, right?
Yeah.
So, like people need to, I assume, to map whatever the problem they have right, into the enrichment.
Yeah, so I'm just going to repeat that question. So the question was about learning curve for Metron. So the observation is that, hey, look, you guys have Stellar, you have your own ways of doing things. You know, you saw that matrix of the different ways to map this. Like, what's the learning curve for Metron? And I think the learning curve for Metron, so if you're used to like a rules-based system, Stellar is not going to surprise you very much, right? I mean, you really saw Stellar. It's function composition with some arithmetic and less than and greater than. So I mean, it should map kind of to what you expect. In fact, I've seen some ArcSight rules, and I would argue, I mean, I may be biased, but I would argue that it's easier, right? The real problem is figuring out, okay, what from an architectural perspective, where should I map this thing that I need to do, right? And that's where the tables, like we saw.
How do we run help in this again?
What's that?
How do we run help in this again? Is it just /H?
No, slash question mark and then tab. No, sorry, not slash, just question mark and tab. The REPL tab completes and it works, yeah.
Whoop. So basically, from the REPL, you get access to all the different functions and everything that you might want to use within the system, and then you can run help on each of these as well.
So to make the learning curve a little bit smaller is aggressive UIs, like constructing UIs around this as well, so that users don't necessarily have to know about the low-level approaches here, but rather be able to work at a more of a use case level. So that's stuff that's coming, but we had to build the baseline first, and then there's going to be layers on top that's easier. But yeah, the other challenge is that we're building on top of big data, a big data stack, and big data approaches look a little bit different than medium data approaches around this. So you'll see things like traditional data mining things coming into play, like sketching algorithms and stuff like that are more at the front, right? That's an artifact of the fact that we do big data. Like those are the kinds of approaches to scaling out those kinds of problems. Yeah.
What are other good venues at this conference for learning more about Metron? And generally, where is the best place to?
Yes. So the question was, where are the other places you can learn about Metron? So the Hortonworks booth has a demo running. I'm giving a talk tomorrow on the profiler. There's a demo today at 5 o'clock by Simon Ball about Metron. There's a Bird of a Feather session after the conference, I believe, that's
There
around
is,
Metron.
and Thursday also, I think they have a workshop session during the day.
Yes, and Thursday there's a
I forget what
workshop
time it
session.
is, but you probably want to check that out because I think it'll be much more like hands-on type of stuff.
Yeah, this is more of a, we're a bunch of engineers, so
Yeah.
you'll get treated probably a little bit better. Yes.
So I'm more curious to learn. Let's say you have false positive and you have all these combinations, right?
Yeah.
And then you get a combination which is not falling within that range.
Mhm.
And here you get actually there are two questions, sorry. So in this case, you have combinations and then you get a query which is not falling inside of that.
Okay.
So how you're going to detect this?
Okay, so the question is, you have a Bloom filter, and we've generated the typosquatted domains. I just want to make sure I'm clear on this. Generated the typosquatted domains, and then you have a typosquatted domain that doesn't fit within our assumptions. At that point, that's an unknown, right? That's something I don't know about that I don't know about, right? So we've built a model that we think is the best that we possibly can, but it has fallen short, much like I fall short in my wife's eyes most of the time, right? You have to look at it with a little bit of disappointment. But we learn from our mistakes, right? So the idea is that once you have made the mistake, maybe you find it because there's another thing that the bad guy, there's another mistake the bad guy makes. And you say, hey, look, this should have been caught in typosquatting. Like, we missed this domain. Then what you do is you can regenerate the Bloom filters, or what you would do is you would regenerate the bloom filters, and in the next 15 minutes, once you've replaced it on HDFS, it'll reread, right? So you catch the error by noticing the mistake, because most bad guys make more than one mistake. That's the good thing about bad guys.
And you upgrade the whole system.
And well, yeah, as the data flows by, it will. Now, rerunning enrichments in batch, we are working toward doing that. That is we're aggressively working toward being able to say, hey, we have these new enrichments we want to run because now we've realized this happened, we want to rerun historical data. Right now, the solution to that is to rerun it through, as a Kappa architecture, through Kafka. That's a bad solution. We want to be able to rerun that in batch with Spark.
Yeah.
So that's, we're actively going toward that. Yeah, no problem. Yeah.
Have you considered using error lookups as an additional data enrichment?
We are always looking for additional data enrichments. Come talk to me afterwards. I'm definitely interested in that. Yes.
Yeah, I want to touch on the system integration perspective, since you have
Yep.
the underlying components like HBase, Kafka,
Yep.
so they're not like lightweight stuff. Right?
No.
So how enterprise can really introduce, if we want to use you,
Yeah.
it should be like the top of the existing big
Yes.
data thing, or it's like a separate. I don't know, like what's the.
Yeah. So we have full Embari integration. We are Hortonworks, so we fully support Kerberos. And if there's something that we do not use in the Hortonworks and the HDP or HDF stack, let us know because we just forgot to use it. Right. So we built on top of Hortonworks. We built on top of HDP and on top of Embari. So hopefully it's a rather seamless approach to that. Now, it's never seamless when it comes to Storm and HBase and Kafka and all these things. But this is a big data problem. So you need to use the right tools for the job. What we're trying to do is to prevent people from having to DIY and create a solution that doesn't work or that falls over. Let us handle the platform, and time is up. Let us handle the platform. Come talk to us later. We'll tell you more about how to handle the platform if you want to. We're going to be at the booth, and we'll be up here for just a minute more.
Yeah. Thank you, guys.
Thanks.